All right, so let's have a look at this one here, guys. So we have velocity versus time graph. First thing they want us to calculate is the displacement of the object. Okay, if I'm going to find displacement, I need average velocity times time. Okay, for the first part, that's pretty easy. Okay, it travels at a constant velocity of 3 meters per second for 4 seconds. How far does it go? 12 meters, right? Average velocity is 3 meters per second times 4 seconds. Okay, this is 12 meters east, according to the axis here, right? Then there's this portion of time where the object is decelerating. Okay, its velocity is decreasing, okay, from 3 to 1 meter per second, and that takes 1 second, right? So the average velocity during that time when it decreases from 3 to 1 would be 2, or half the height of this triangle multiplied by the base of this triangle. Would that give me the displacement? Okay, so I'm going to have the height of this triangle is 2 divided by 1, or sorry, divided by 2 is 1, multiplied by 1, so this basically is just 1 meter, okay, east. Everybody okay with that? All right, and then there's this portion here that represents how far the object would travel if it traveled at that remaining 1 meter per second for the last 6 seconds here. All right, so that's going to be 6 meters. Right? So our total displacement here is going to be 19 meters east. Okay. Everybody all right with what I did there? And I calculate the area between the line and the x-axis. Okay, and that's what we're supposed to do because that's average velocity times time. Okay, that gives us displacement. Okay, questions on what I did there? All right, now how do I calculate acceleration? Okay, it can be the slope, but I don't have one single sloped line here. Okay, is there another way to calculate acceleration? Change in velocity over time. This formula you used and learned in Science 10. Okay, that calculates average acceleration. Right? The final velocity of the object is 1 meter per second. Okay, the initial velocity of the object is 3 meters per second, and that happens over 10 seconds. All right, so we got 2 over 10, so the acceleration is going to be negative 0.2 meters per second squared. Okay, actually, it's going to be not negative, it's going to be west. Okay, because negative east is west. It's like negative right is wrong. Or left, depending on the situation. All right, everybody okay with what we did there? Right, so sometimes you're going to use like slope stuff, sometimes you're going to use y equals mx plus b, and other times you can just use your formulas. Okay, it'll kind of depend on the question and the situation. Okay, if a question specifically asks using your graph and the equation given with it, so it gave you a y equals mx plus b, should you probably do the question that way? Yes, you should. I only say that because that's usually how I ask something on a quiz or a test. Okay, if I want to make sure I'm assessing what I want, I tell you to do it this way, and I expect that you do it that way. Okay, if you don't, you won't get it right, and that will suck for you. Okay, so I'm not trying to trick you if I ever tell you on a question, do it this way. Don't think outside the box on a question like that. It's not a think outside the box kind of question. Okay, would these ones be a little easier? Calculating displacement. Okay, do I only have one shape to worry about on these questions? Okay, so if I want to calculate the displacement on this graph here, okay, we're traveling at 2.2 meters per second for 10 seconds. How far does it go? 22 meters. And that's north, okay, according to that graph. Okay, what's the acceleration? 0. Okay, and I don't need to do a calculation to figure that out because a flat line on a velocity time graph tells me the velocity is constant. It's not changing. Okay, that's one of those recognition things. On a test, okay, I've done this in the past. I've shown a graph where there was no acceleration, okay, and asked people, what is the acceleration? And I say it that way. I don't say calculate it. I ask what it is. Okay, for 1 mark, and people will show me 6 or 7 marks worth of proof that's all wrong. Okay, come up with a number that's all wrong when the answer is 0. Okay? So always look for what a question is out of. It usually gives you a pretty good idea of how much work you should do. Okay? It's a 1-mark question. The answer is probably right in front of you and doesn't require a page and a half worth of proof. Okay? Everybody with me? These are just test taking tips for later. Okay, for question number 2 here, using the graph below, determine the displacement of the object. All right, so in this one, what's the object doing here? It's accelerating negatively. In this case, that would be in which direction? West. Okay, it's accelerating west. Okay, so we want to calculate its total displacement. Okay, well, it goes from 0 to negative 20 meters per second. Right, so its average velocity would be negative 10, okay, and so that would be our base times height over 2 calculation. So negative 10 times 10 tells me this thing went negative, or actually 100 meters west. Okay, the way they've written it here, they actually wrote negative east. Okay, I would never say that Calgary is negative south from here. Nobody talks that way. Okay, you should never write an answer as negative north or negative south. It's dumb. Okay, don't write it that way. All right. I want you guys to try this one here. Okay, so we've got this graph. It's of a bird. Okay, and I want you guys to see if you can do A, B, and C. Okay, so from the graph, determine whether acceleration is positive, negative, or 0 in each section. So you can just write in A, is it positive or negative? In B, is it positive, negative, or 0? C, and so on. Okay, the value for the acceleration anywhere it's not 0. Okay, and when the bird changes direction. Okay, when the bird changes direction. Give you a couple minutes on that. What I mean by when is what time on the graph does the bird actually change directions from flying south to flying north. All right, so in part A, is the acceleration positive, negative, or 0? It's negative. The velocity is becoming more negative during part A. What is it in part B? 0, right? The velocity is unchanged during part B. In part C, the acceleration is negative. Okay, part D, 0. What about part E? Positive. Part F? 0. Okay. Now, the second part is they want to calculate the value of the acceleration where it is not 0. Okay. Well, we just reviewed that we have a formula that calculates acceleration. Okay. And remember, we saw yesterday that that's actually a slope calculation from this graph. Okay, because we got velocity on the y-axis, we got time on the x-axis. So really, what we're doing is calculating the slopes of all these diagonal lines that are on the graph. Everybody okay with that idea? All right. So in part A, we go from negative 2 to negative 4. Okay, so negative 4 minus negative 2. Okay, so we're going to have our change in velocity being 2 meters per second divided by the time, which was 1 second. So we'll have negative 2 meters per second squared on that one. Okay, everybody all right with that? Okay, and then we've got for part B, obviously it was 0, and then in part C, we go from negative 4 to negative 6, and that takes, again, 1 second, so we're looking at exactly the same rate of acceleration as in part A. Okay, in part E, our initial velocity is negative 6, our final velocity is positive 6. Okay, so negative 6 minus positive 6, we've got 12 there, right? Okay, and we're dividing that by the time. That took 2 seconds. Okay, so we're looking at an acceleration of positive 6 meters per second squared. Okay, everybody all right with that? Okay, and then for our last one, obviously it was 0. Okay, at what time, does the bird change direction? Okay, where in E? Like at exactly what time on the graph?
7 seconds.
Okay, so 7 seconds is the answer I usually get from people. Okay, but here's the thing we have to recognize. Okay, we see the line change direction, which means the acceleration has changed from being 0 to a positive value. But is the bird still flying backwards there?
Yes.
Yes. Okay, the bird's velocity here is still negative, which means it's still flying backwards. It's flying backwards until there. Then its velocity becomes positive, and now the bird is flying in the other direction. Looks weird on the graph, okay? But that's how we have to interpret it. Okay? The bird is flying backwards until 8.5 seconds. Okay? At that point, its velocity is 0, okay? And after that, it becomes a positive value. So now the bird is flying in the other direction, okay? Actually flying north as opposed to south. So what this would look like would be the bird is kind of turning during this section. Okay, it's turning around, so its velocity south is changing to a velocity that is becoming more and more north. Right? It's hard to imagine that with a bird because a bird can't do this. Okay, this graph is really just showing something that's actually just like stopping and then going the other way rapidly. Okay, obviously a bird doesn't do that. Okay? But that's what the graph shows. All right, everybody follow me on that one. I almost always have a question like that on my unit exam. Okay, as an interpretation of a velocity versus time graph question. Okay, so make sure that we understand what we're seeing in this graph. We're seeing a bird that's flying in a negative direction for a period of time and then in a positive direction for a period of time. Okay. All right. What is going on in question number 1 here? Remember that this is a position versus time graph now. Okay. What is the object doing during this part of the graph? Moving at a constant velocity north. Okay? It's saying it's giving us the direction of being north here. Okay? So because this is a position versus time graph, the position is changing at a constant rate. What's the object doing here? Standing still, right. Okay, what's the object doing here? Going backwards at a constant velocity. Okay, same here, same here. Now, in one of those two sections, is it going faster than the other? Yes. Okay, but still going backwards in both of those sections. All right, I would like for you guys using that graph to calculate for me the average, well, first off the total displacement because you'll need it, and then the average velocity of the object. Okay, so total displacement and then average velocity. So average velocity is total displacement divided by total time. So negative 12 divided by 10 seconds. Okay, we're looking at 1.2 meters per second south. Okay, so V equals D over T. Okay, negative 12 over 10 is 1.2 meters per second south. Right? Okay. Calculate for me from that graph now the total distance and the average speed. All right, if I'm going to get the total distance traveled, I need to know how far it goes in each part. Agreed? All right, so it goes 6 meters, 6 meters, 12 meters. Total distance, 24 meters. Okay, average speed is total distance over total time. 24 over 10 gives me an average speed of 2.4 meters per second. There's no direction on that because it's a scalar quantity. Okay. Looking at this velocity versus time graph, what's happening in this part of the graph? Constant velocity. Okay, what's it doing here? Right, its velocity is actually 0 here. Okay, right? It's just actually at 0, so it's moving at a constant velocity of 0 meters per second. Okay, and then here it's constant velocity of like negative 3. Okay, and then a constant velocity of negative 6 or so. Okay, everybody with me on that? Okay, now is there a relationship between the first graph and the second graph? Are they showing similar things? Okay. In this first part of the graph, we go 6 meters in 2 seconds. Okay. And here, we were going 3 meters per second for 2 seconds. And then we were stopped. Okay. And then we went in a backwards direction. Okay. For quite a while, actually. Okay. This whole thing here, okay, is the same velocity all the way back. Okay, and then this short period of time where we went even faster in a backwards direction. Okay, these two graphs are showing exactly the same thing. Okay? They are of exactly the same motion. Right? They look very different, obviously. Okay? Now, what this graph here is showing is actually an impossibility. Okay? You cannot instantaneously change your velocity from one velocity to another, which is what this graph is showing. Okay? It's saying the object magically jumped from 3 meters per second to 0. Okay? It stopped instantaneously. That doesn't happen. Okay? You could have a slanted line. It could be really, really steep, but it would have to be slanted. Nothing stops in no time. Okay? All right. Okay. I would like for you guys to calculate for me the total displacement for graph number 1. Okay, so don't worry about part B. I just want you to calculate the total displacement. Okay, this line here, this is 10 seconds. Okay, right here. Okay, so if I want to calculate total displacement, I want to use average velocity times what? Times time. In other words, I'm finding the area between the line and the x-axis. Okay, so for here we go 5 meters per second for 10 seconds. So that's positive 10 meters. Okay, and then here we go negative 5 meters per second for 8 seconds. Sorry, that's 50 meters. Answer's 10. I had that in my head. Okay, that's my excuse and I'm sticking to it. Then this one's going to be negative 40, which, okay, adds up to 10 meters positive or forward in this case. Okay, so our total displacement is 10 meters forward. All right, everybody okay with that? That's a pretty simple one. Okay. All right. I'd like you to try 7 and 8. Okay, give 7 and 8 a try there. Okay, we'll go through those in a minute. All right, so for number 7 here, okay, determine the displacement of the object in this graph. So I'm going to have essentially 2 shapes to calculate here. I'm going to have this rectangle underneath this triangle here. So this rectangle represents what the object would have done if it had stayed traveling at 5 meters per second for the entire 10 seconds, and that is that it would have traveled 50 meters. Okay? However, at time 5 seconds, it accelerated from 5 to 15 meters per second. Okay? So I've got to take the average velocity, okay, and multiply that by the time. Okay? So my height of my triangle is 10, okay, from 5 to 15, okay, multiplied by 5 seconds. Okay? So I'm going to have 5 times 5, so this is going to be 25 meters here. Okay? Everybody all right with that? All right, so my total displacement there is 75 meters east. Okay? And then, for this graph here, calculate the displacement from the velocity versus time graph below. Okay? So we've got, we're traveling at 4 meters per second for 5 seconds. Okay? So that's going to be 20 meters there. Okay? And then we've got this portion where we only go 2 meters per second for another 2 seconds. Right? Yeah, so that's going to be 4 meters there, and then we go 5 meters per second for the last 7 seconds, so that's another 15 meters. Okay, so we're looking at 39 meters, or 39 kilometers up, because this is kilometers per second. That's fast. Okay, it's a rocket or something. Okay, so we would say 39 kilometers up. Would be our overall displacement there. Okay. All right, now something that comes up, because I see this happen sometimes. People are drawing a velocity versus time graph, okay? And it says an object travels at a constant speed for like 10 seconds, so they draw it like this, and then it says, then it turns around and goes back for another 5 seconds, and I see people do this. Okay, what's wrong with that?
You're going backwards in time.
Right, you're going back in time. You're going backwards and backwards in time. Okay, so I don't know, maybe you're driving in, an 85 DeLorean at 88 miles an hour backwards, but okay, you are definitely not going back in time. Please never show a graph where you reverse along the x-axis, because you're doing something that, at least as far as we know, is physically impossible. Okay, and that is to go back in time. Okay, your graph needs to always go forwards, even if your velocity happens to be negative. Okay, it's still got to go that way. Okay, forwards in time. You should never have a piece of graph overlapping each other on the x-axis. Okay. All right. Not that one. And not that one. You know what? I have it here. This is the ones I want you to do. Okay, from your digital workbook, I want you to work on a couple of these here. Okay, where it asks you to draw the graph yourself, just do a rough drawing. It doesn't have to be to scale or anything, just as long as you can get the numbers you need from it. It doesn't need to be a perfect, beautiful graph. Okay, so I'd like you to try number 6 and number 7 and let's say number 9. So 6, 7, and 9 for right now. Let's have you working on those. Okay, and then we can go through those as we go along here. All right, so it wants to know the average velocity during each of the segments. Now, there's 2 ways to go about that. There's the way to actually calculate it, which is to calculate the displacement in each section and then divide that by the time, or we can just look at the graph and kind of commonsensically figure it out. Okay, if I increase my speed or velocity from 0 to 40, my average would be 20, halfway in the middle. Okay, here I'm traveling at a constant velocity of 40, so my average velocity would be 40, right? Doesn't require any calculating there. And in here, I change my velocity from 40 to 80, so my average would be 60, halfway up, right? It's always halfway is the average point. Now, to do the total, though, I can't do it that way. Okay? To do the total average velocity, I need to know the total displacement and divide it by the total time. Right? That means calculating the area of all the shapes on the graph. So that would be this triangle, okay, this rectangle here, and then that triangle up top. All right, so on this one here, we got 40 times 20, which is 80 over 2, okay, not 80, 800 over 2, okay, which is 400, okay, and then we have 40 times, I'm just going to say it goes to here because that's where it goes on your graph, okay, 40 times 30, so that's going to be, 1,200 meters, okay? And then here, sorry, it's got to go all the way to the end. That's why it didn't seem right to me in my mind. Okay, so we got to go all the way to the end. So from 20 to 60, so that's going to be 40. Okay, sorry. So I got 40 times 60, so this is going to be 2,400. Yes? Okay, meters, and then I've got this triangle here, okay, that's got a base of 10 and a height of 40. 40 times 10 is 400 over 2, this is 200, okay, add them all together, I've got my total displacement divided by 60, I've got my average velocity. Everybody all right with what I did there? Okay. How are we doing with number 7, where you have to draw your own graph? How many people have done number 7? Okay, I'm going to give you a little more time on that. The whole reason I told you not to go back in time was for question number 7, because that's where people usually draw going back in time. Okay, you do have to do one kind of intermediate calculation in number 7. Okay, you don't know how long it takes them to walk back to the car. Okay, but you do know how fast they walk and how long it takes to walk from the car to the gas station. So you should be able to figure out how far the gas station is. It's the same distance back to the car, even though you're carrying the full can of gas, right? So there's a little intermediate calculation you have to do there. Okay, that ends up looking like this for our velocity versus time graph anyway. Okay, first we travel at 25 meters per second for 10 minutes. Okay, so that's this part of the graph right here. Okay, then the car runs out of gas and the person walks at 1.5 meters per second for the next 10 minutes, which is another 600 seconds. Okay, then they have to walk back, but now that they're carrying the big heavy can of gas, they walk a little bit slower. What I don't know is how far it is from the car to the gas station. And I need to know that so I know how long it's going to take them to walk in terms of seconds, okay, to get back. So what I have to do is find the area underneath the line for this section, because that would be the displacement from the car to the gas station. Everybody follow my logic there? Okay, so I'm going to have 1.5 meters per second times 600 seconds, which is going to give me 900 meters. All right, so it's 900 meters from the car to the gas station. Pretty lucky, okay, that they only had to walk less than a kilometer, okay, to get to the gas station. All right, so now that I know this person has to walk 900 meters at 1.2 meters per second, I can calculate how long it will take them, so I know how long to make that line for their return trip to the car. So that's that intermediate calculation that you have to do here. So 900 divided by 1.2, okay, is going to give you the amount of time required to get back. Okay, so it's going to take 750 seconds instead of 600 seconds to get back to the car. So we draw the line that length, and then they travel back home. Okay, so 25 meters per second, okay, for another 600 seconds, and they're back home. All right, everybody okay with that graph?
Are we not supposed to include the 5 minutes? Maybe we can.
Oh, yes, you probably should. So there should have been a flat part in there, yeah, along at 0. Yeah, I skipped that. You're right. Yeah, there should be a 5-minute stretch where they're just at 0. How many people remember that? See, you're all smarter than me. What are you doing in here? All right. How are we doing with, how many people are done number 9? Because I didn't say to do 8, I said to do 9 next, right? So maybe we'll make it so you can see number 9. Okay, so we got another velocity versus time graph, and we're looking for the distance the object travels between 0 and 5 seconds, between 5 and 10, 10 and 15, 0 and 25. Okay, we'll see how that one goes, and then we'll start looking at what we're going to be doing tomorrow probably.